Chemical Engineers, Lecture 1 I should say. What do we do in engineering maths? I'll be teaching you the phenomena, the maths of a I'll be teaching you a concept branch of maths which we call calculus. Calculus is the maths of differentiation and integration. For that we will be studying some certain stuff like basic differentiation, differentiation in part 2, differentiation part 3, applications of differentiation, part 2, and then after that we move to a different topic which is integration, that is the counter of differentiation, and we will be studying integration, simple integration, advanced integration, higher level, application of integration 1, applications of calculus. That is, you have to differentiate and integrate together, and we'll be studying how calculus relates to chemical engineering. All the work that we do over here in calculus will be related to chemical engineering. For example, rate of deriving the formulas for resistances, heat resistances, fluid flow, on differentiation and integrations in fluid flow. That's the last part. That's when you would have learned fluid flow, that we will do all that stuff. But we do differentiation and integration for right now. What is differentiation? It's nothing. It's like if I have this. If I have, for example, this book, it's a Wilson and Richardson. If I have this book and I cut it into pieces, I get small pieces. I cut those smaller pieces into small pieces, and I keep cutting those smaller pieces into smaller pieces. I cut this book into 1,000 million parts. I cut those million parts into million parts again, so gives me 10 to the power 12. I cut those 10 to the power 12 in million again, I get 10 to the power 18 parts. And I keep going until I get a very, very small thing. That small thing of this is what we call an element. It's denoted as D object. It's denoted as D object, which you can see I've written over there. D object. D object is the small, very small part. Right now our differentiation will be on not on real objects but on mathematical things. So we will be differentiating graphs. For example, I have this kind of a graph. This is my graph on a Cartesian coordinate. My graph on a Cartesian coordinate. This is this is y-axis. This is x-axis, and this is my graph. Now if I divide this graph into various small parts, and I take this small part over here, this is the x, and over here it is dy. Placing it here so you can see where dx and dy are. This is dx and dy. Okay, so I have here my graph with dy here and dx here. What I'm going to do is, there's very, very small parts, x and y. It is this part of the graph. So I'll take that part and think about that part, and thinking about that part, I will then integrate it to get the whole part. That is, if this small part behaves like this, then if I integrate this, how will the whole behave? Because the chemical engineers would count different molecules. A portion of a molecule is not counted by chemical engineers. We calculate large quantities. Large quantities are integrals, that is many small dots put together will give us one large quantity. Like many atoms put together give us a molecule. Like that, many small dots put together, small parts of the graph put together give us the actual graph. So that's it. Now we know what slope is equal to, and from this graph, which I've drawn here, which you can see, slope will be equal to dy by dx. So dy by dx is the slope, and this slope, the slope which I've written here as dy by dx, this is what we call differential of y with respect to x. So how do we define differential? Differential is the slope of y versus x graph, slope of y versus x graph at the given x, at the x is given as dy by dx. You have all learned of some myriad of calculus, some parts of calculus. At least you've learned a thing called first, what I'll be teaching you today. I don't know if you've learned or not. It's called fundamental first theorem of calculus, or the first theorem of differentiation. It's also the, why is it called the fundamental theorem of calculus? Because it is what uses this definition to calculate the differentials of different functions. So what is this first principle of calculus, or fundamental rule of calculus? It is given by the following equation. If I have this graph, I have this part as fx, over here y is fx, over here y is f of x plus dx. Okay. Y f of x plus dx. So if I say that, if I need to calculate the differential, it is dy by dx is equal to fx plus h minus fx over h over x. But like I told you, over here h has to be very small. Those are very small parts. 1 into 10 to the power 18 parts of the book. Remember, more than that, 1 into 10 to the power 24. So we define dy differential of y with respect to x as limit h tending 0, that is h goes towards 0, f of x plus h minus of fx over h. That is what we call the fundamental theorem of calculus, that dy by dx is equal to limit h tending 0, fx plus h minus fx all over h. So why was fx actually over here? I considered y to be fx. Sorry, I didn't write that assumption. Very good, you pointed that out. I'm very happy you should point stuff like this on. I forgot to write that y is equal to fx. Okay. So now we'll be deriving differentials of different functions. We start by deriving differential of, let's say, 10x. Y is equal to ax. If we have y is equal to ax, which I've written over here. Y is equal to ax. I say that dy by dx is equal to a x plus h, limit h tending 0, minus a of x all over this is what I write. Solving this is very simple to derive that d of ax by dx is equal to a. That is what we call our result. D of ax by dx, that is differential of ax with respect to x, gives us a. That means if we have a constant into x, we get the constant, that is we just remove the x. As simple as that. It's also shown by the graph. The graph will be y equal to ax will be like this, and the slope will be equal to a. The graph will be like this, drawn at that end. The slope equal to a, and so we know that dy by dx should be equal to a, obviously. And that follows with common sense. Similarly, if y is equal to c, dy by dx will be 0. That is, a differential of a constant is 0. A differential of a coefficient term, the coefficient of x with a coefficient is the coefficient itself. So this is, the coefficient is not there over here. Now we'll go into some greater depth. We shall calculate the differential of x to the power n. We have x to the power n, so we have d of, so I have here d of x to the power n by dx is equal to limit h tending 0 f x plus h to the power n minus x to the power n over h. You can see it here. Now let's think it to be squared. Let's assume, since, do any of you know binomial theorem, huh? To expand x plus h to the power n. Anyone knows the binomial theorem? No? Okay. Then just assume that n is equal to 2. So if we assume n is equal to 2, then we get x squared plus h squared plus 2xh minus x to the power n over h. These get cancelled. We get limit h tending 0, and we calculate that, so we get limit h tending 0 of h plus 2x is equal to 2x. So that you can see it. See how we worked. A similar thing can be done for assuming n is equal to 3. We do a similar thing, that is, we assume n equal to 3, we do x plus h cube minus x cube, that gives us x cube plus h cube plus 3xh x plus h, or 3x squared h plus 3x h squared. Okay, and we divide everything by h after cancelling x cube, and we get the only term remaining will be the terms remaining after that you get as 3x squared plus 3xh, and you get 3x squared plus 3xh plus h cubed plus h squared, sorry, and putting h equal to 0 we get 3x squared. Assume n equal to 3, so I can write it as assume n equal to 3, d of x cubed by dx gives us 3x squared. We can easily derive this. 3 d of x cubed by dx is just 3x squared. Now, what do we note over here? Do you note anything? The n. What's happening to the n? The n is coming on as a coefficient. When n was 2, the coefficient was 2. When n was 3, coefficient was 3. So, n is same as the coefficient. So we can say that, we can conclude it by saying that d x to the power n over dx is given by n times x, and what do we see? The power of x is actually 1 less than the power it initially had. So it is just n x to the power n minus 1. D of x to the power n over dx gives you n times x to the power n minus 1. So if n is equal to 1, we get, if n is equal to 1, that is x, we get 1. So we can also say that d of a to the power a into x to the power n over dx gives us an into x to the power n minus 1. If you followed me through and understanding how we are working with this formula, we do x plus h minus what was x for y for x, we do y for x plus h minus y for x, and we divide it by h and we put h equal to 0, and we get an answer. That answer is what we call a differential. So far so good. We haven't ventured into the good difficult stuff till now. We've done polynomials, we've done algebraic, that is coefficients and all that stuff. Now we want to move into, now let's go on to other functions. Let's go on to trigonometric functions. Okay, let's go back to trigonometric functions. Let's go to trigonometric function. Let's see how trigonometric functions work. Sine of x plus sine. Let's take sine for example. How does sine work? How does sine work? We have d of sine x by dx. Now I have to find d of sine x by dx. I can easily do it. We say is equal to limit h tending 0 sine of x plus h minus sine x all over h. You write sine x plus h as sine x cos h plus cos h sine x plus sine h cos x, right? Sine x cos h plus cos h plus sine h cos x minus sine x. You take sine x cos h plus cos h plus sine h cos x minus sine x over h. You simply take this sine x common, you get sine x cos h minus 1 plus sine h cos x over h for h. Okay, now you use, this is what we've done so far. See what has happened so far. Now all you have to do is, once you reach this step, you apply the formula for limits here. In this part you get limit h tending 0 sine h by h is equal to minus 1, and you get minus cos x is equal to 1, and you get cos x over here, and you have over here you have sine x into cos h minus 1 over h, limit h tending 0, cos h minus 1 over h, h tending 0 gives you 0, so this becomes, this whole term becomes 0, and you get your answer as cos x. So you can see what happened. If you want to note down the steps. Similarly, if you want to calculate for cos x, you do cos x plus h. Differential of cos x is cos x plus h minus cos x over h. You get cos x cos h minus sin h sin x minus cos h whole over h. Again you take cos h common, you get cos, you take cos x common, you get cos x into cos h minus 1 over h plus sin h minus sin h over h into sin x. You again do you know cos h minus 1 over h will give you 0, and sin h over h gives you 1, limit h tending 0, and you can calculate After that you can work out, you'll get the answer as minus sin x, that is d of cos x over dx is equal to minus sin x. And you get minus sin x. Good, isn't it? Excellent. So you can do the similar for tan. You know the formula of tan x plus h. You put tan x plus h, you use formula of limits, and you will get the, you rearrange, you use trigonometric formulas, you will get x square x. If you have any problem, we'll discuss it in the next class. Similarly for all others, you can do it and find the answers. If you encounter any problem, tomorrow during our next lecture tomorrow, we'll discuss it. Now what is left? What kind of functions are there? Linear, done. Polynomial, done. Power, yes, polynomial itself, done. Trigonometric, done. What is left? Exponential, that is like e to the power x, or in general e to the power of x. And also what is left? Logarithmic functions, log x, functions like log x, and they are left. I'll derive e to the power x for you. A to the power x, I'll derive a to the power x, e to the power x, and the logarithmic functions I want you to find on your own. If you have any problem, we'll discuss them also tomorrow. This won't be asked in your, you won't be tested on this, but I have to tell you how you get all the derivatives. So we are going to do it for e to the power of x first. D of e to the power x over dx is e to the power x a minus plus h minus e to the power x over h, limit h tending 0, is equal to e to the power x, e to the power h minus 1 over h is equal to limit h tending 0, where limit h tending 0 e to the power x. Yeah, so what is e to the power h? Minus 1 over h. It is 1. E to the power h minus 1 over h. We use Taylor series. If you want, you can use it, and you derive that it is 1, and you get the answer as e to the power x. One answer. Differential of e to the power x is e to the power x. The differential of the differential of e to the power x will also be e to the power x, and it will continue to remain e to the power x till infinity. You understand? Now we'll do it.